Something is happening inside the world's most powerful computers, and it is starting to break everything we thought we knew about speed, heat, and even how computation works. For decades, GPUs have been the backbone of artificial intelligence. Every image generator, every chatbot, every large language model, all of it runs on graphics cards originally designed for video games. But now in 2026, we've hit a wall. Not a software problem, a physical wall. Power consumption is exploding, heat is out of control, and no matter how many transistors engineers cram into silicon, performance gains are slowing down. And right in the middle of this slowdown, a completely different kind of processor has quietly entered a real, working supercomputing center in Germany. A processor that doesn't really compute with electricity at all. It computes with light. And according to the company behind it, performance isn't just better, it's radically different. We're talking claims like 3,000% higher efficiency and up to 5,000% higher compute performance compared to traditional GPUs. But here's where it gets even more interesting. This isn't a lab experiment sitting behind glass. It's been packaged into a standard server format and deployed into a real high-performance data center. So the question is simple. Is this the beginning of the end for GPUs, or just another overhyped breakthrough that can't survive real-world computing? To understand that, we first need to understand why GPUs are struggling so badly in the first place. Because the truth is, the GPU isn't failing due to lack of innovation. It's failing because physics is starting to push back. One of the biggest issues is something engineers call the memory wall. The memory wall is the growing gap between how fast processors have become and how slowly memory systems are improving in comparison. In simple terms, GPUs can calculate insanely fast, but they are constantly waiting on data to arrive from RAM, and that waiting kills performance. Modern AI workloads are extremely memory heavy. Every neural network layer depends on constantly moving massive amounts of data back and forth between compute units and memory. So even if your GPU is extremely powerful, it's often sitting idle, waiting for data instead of actually computing. And that gap is getting worse every generation. Then comes the second major bottleneck: heat and energy efficiency. A GPU consuming 500 watts doesn't just use 500 watts. Nearly all of that energy ends up as heat. Not because something is broken, but because of how computation physically works at the electronic level. Electrical resistance inside silicon creates heat as electrons move through transistors and wiring. And the more complex the chip becomes, the more heat it produces. That heat then forces limits on clock speeds, chip density, and even data center scaling. This is why modern AI training clusters feel like giant industrial cooling systems rather than computers. And this is where things get fascinating, because the new approach doesn't try to fix electricity-based computing. It replaces it. A company called Quant has built what it calls a native photonic processing unit. Instead of using electrons moving through silicon, it uses photons, particles of light. And here's the key difference. Photons don't have mass. They don't experience electrical resistance in the same way electrons do, which means, in theory, they can carry and process information with dramatically less heat generation. But this chip doesn't just send light through a circuit in a simple way. The core material is something called thin-film lithium niobate, a crystalline structure designed to manipulate light at extremely precise levels. Instead of transistors flipping on and off, data is encoded into laser beam. Once the data is inside the chip, the light is split, bent, and modulated across multiple optical paths and frequencies. And this is where computation stops looking like traditional computing. Because instead of performing math, step by step like a CPU or GPU, the chip uses physics itself to do the work. Here's what that means in practical terms. On a traditional GPU, if you want to compute something complex like a transformer model layer or a non-linear function, the system breaks it into millions of small operations. Each operation is executed across many clock cycles using transistor switching. It is powerful, but fundamentally sequential and energy-heavy at scale. On a photonic chip, the same data is sent through specially designed optical structures. As different wavelengths of light intersect, they naturally create interference patterns. And those interference patterns are not random. They represent the solution to the computation. In other words, the math doesn't get computed step by step. It emerges instantly as a physical outcome of how light interacts. That is the core idea behind photonic computing. Instead of forcing hardware to simulate math, it uses physical laws to produce the answer directly. And because photons don't generate electrical resistance like electrons, the heat problem is dramatically reduced. This is why claims like massive efficiency gains are even being discussed seriously in the first place. But theory is one thing. Real-world deployment is something else entirely. And this is where things get even more interesting. The photonic processor has already been integrated into a standard 19-inch rack-mounted server system and deployed at the Leibniz Supercomputing Center in Germany, part of a major European high-performance computing environment. This matters a lot, because supercomputing centers don't test hype. They test reliability, integration, and real workload performance under extreme conditions. And the surprising part is how normal the hardware actually looks. The photonic processor is designed as a PCI-compatible card. That means it can plug directly into the same server infrastructure used by traditional GPUs. No exotic redesign of entire data centers, no completely new computing architecture required, at least on the surface. But hardware is only half the battle, because GPUs didn't dominate AI just because they are fast. They dominate because of software. Entire ecosystems like CUDA, PyTorch, and optimized AI frameworks are built around them. So if photonic computing required developers to learn optical physics just to run a neural network, it would never survive outside research labs. To solve this, Kant built a software bridge called QPAL, the Photonic Algorithm Library. QPAL acts like a translator between standard AI code and photonic hardware. Developers can still write models in Python and PyTorch, exactly the same way they do for GPUs today. Under the hood, QPAL converts those instructions into optical operations that the chip can execute using light. This is critical, because without software compatibility, even the fastest hardware is useless in real-world AI development. So where is photonic computing actually being used today? Right now, photonic processors are still in the early evaluation stage and are mainly targeted at extremely compute-heavy, specialized workloads. This includes real-time medical imaging, advanced climate and weather modeling, and large-scale visual AI systems where traditional GPUs start to hit limits in power consumption and memory bandwidth. But despite the excitement, there's a major limitation, and it's a fundamental one: the memory wall. Photonic chips, like those being developed by companies such as Kant, are extremely fast at computation, but they cannot store data internally the way electronic chips do. That means AI model weights, cache data, and outputs still depend on conventional electronic memory like VRAM and system RAM. This leads to what engineers call a conversion penalty. Every time data moves from electronic memory into a photonic system, it has to be converted into light. Then, after computation, it must be converted back into electrical signals again. These repeated conversions add latency, consume energy, and reduce some of the raw speed advantage that photonics is supposed to deliver. In workloads where data constantly moves between memory and compute, this overhead can significantly reduce the overall gains. Because of this, photonic chips are not replacing GPUs. Instead, they function as specialized co-processors, handling the most mathematically intensive parts of AI workloads while CPUs and GPUs continue managing memory and system coordination. The long-term breakthrough researchers are aiming for is something called a photonic latch, an optical equivalent of memory like SRAM. If successful, it could allow light to be stored temporarily inside microscopic structures, enabling both computation and memory to exist entirely in the optical domain. That would eliminate constant electrical conversion and could completely reshape computing architecture. If that future arrives at scale, it won't just make systems faster, it could redefine computing itself, shifting it from electricity-based processing to light-based processing. For now, GPUs still dominate AI hardware, but they are no longer alone at the top, and photonic computing is quietly becoming a serious contender for the next generation of AI infrastructure.